Dear children, now we will learn second application of Gauss law. First application, electric field due to uniformly charged infinite long wire we have completed. Now come to the second application, that is electric field due to uniformly charged infinite plane sheet. So let us consider a plane sheet. You consider this plane sheet is infinite, means its extension is infinite, means length is infinite and also breadth is infinite. So you know, when you apply Gauss law, you have to consider a Gaussian surface. So here we have imagined a Gaussian surface in the form of a cylinder. It is the Gaussian surface. Now in this cylinder you have two flat surfaces S1 and S2 and one curved surface, that is S3, and I have taken this plane sheet is positively charged. So then for the surface S1, what is the direction of the electric field due to this plane sheet? That is away from the sheet, so that is along right. And for S1 surface, what is the direction of the area vector? That is along outward drawn normal. You see here both electric field and area vector, they are parallel to each other. Similarly, for this face or this flat surface S2, then you see electric field is towards left, direction of the electric field, and area vector is along outward drawn normal. Again you see electric field and area vector, they are along same direction, that is parallel to each other. But for curved surface you see that the electric field for this point, electric field is towards right and area vector, that is upward. So what is the angle between them? 90 degree. And you see here electric field is towards left because it is positive charge, that is away from the charge. And for area, what is the direction of the area vector at this point? That is upward. What is the angle between them? 90. If you say what is the angle between the electric field and area vector at this point, it is the direction of the electric field and it is the direction of area vector. What is the angle between them? That is also 90. Similarly, for this point also, it is the direction of electric field and it is the direction of area vector. What is the angle? That is 90. So you got here for the two flat surfaces, electric field and area vector are in the same direction. The angle between them is 0 degree. But for curved surface, electric field and area vector, they are perpendicular to each other at every point on the curved surface. So now come to determine what is the electric flux by integration method by surface integral of electric field. So I is equal to E vector dot S vector over the closed surface, that S indicates it is the surface integral. So this cylinder will be the closed surface by taking these two flat surfaces S1 and S2 and one curved surface, that is S3. That is E vector dot S vector for S1, then E vector dot S vector over S2 and E vector dot S vector over S3. Individually S1, S2 and S3 are not closed, that's why I have not marked closed sign on these integrations. So for the curved surface, just we have discussed the angle between electric field and area vector is 90 degree, they are perpendicular to each other, so that dot product is 0. So from equation 1, as it is 0, it becomes phi is equal to E vector dot S vector over S1 plus E vector dot S vector over S2. And for S1, the angle between electric field and area vector is 0 degree, and also for S2. So I have marked here, it is EDS cos 0 degree, also it is EDS cos 0 degree, it is over the surface S1 and it is over the surface S2. And as E is constant, that can be taken out. These two faces are symmetrical to this plane sheet. That's why electric field at this point and electric field at this point is same in magnitude. So E can taken out, then ds integration, also E can taken out here, ds integration, and ds integration is S. So it is E into S, and for this it is E into S, that is 2ES. What is S? S is the flat surface area. So here we got electric flux through the whole imaginary cylinder is 2ES. So now you apply Gauss law. What is Gauss law? Applying Gauss law, Gauss law, phi is equal to Q by epsilon 0. Here, what is Q? Q you know, that is the charge enclosed by the Gaussian surface. So you see, if the cylinder is the Gaussian surface, you see first what is the portion of this plane sheet enclosed within this Gaussian surface. You see, this is the portion of this plane sheet cut by the Gaussian surface. Then what is this area? It is same as the flat surface area, that is S. And as it is plane sheet, the charge distribution is surface charge distribution, and you know surface charge density is sigma. So Q you can write, that is sigma into S by epsilon 0. What is sigma? Sigma is surface charge density, and what is S? S is the area, that is flat surface area, that is the area of the plane sheet cut by this Gaussian surface. So it is your equation number 3. So now you compare equation 2 and equation 3 from equations 2 and 3. Here it is 2ES. In both the equations you have LHS is same, so we have to make RHS equal. That is 2ES is equal to sigma S by epsilon 0, or E is equal to sigma by 2 epsilon 0. So you see, it is the expression for electric field due to plane sheet, infinite plane sheet. So now, how it depends upon distance? You see from this expression, you can conclude that the electric field due to uniformly charged infinite plane sheet is independent upon the distance. So, how can you write in vector form? In vector form, E vector, you see this electric field is along the direction of n cap, that is along the direction of the area vector. So you can write E vector equal sigma by 2 epsilon 0 n cap. It is the equation number 5. Now we will draw the graph between electric field versus distance. It is electric field and it is distance of the point from the sheet. And as you saw here, E is equal to sigma by 2 epsilon 0. Here it is here in the expression there is no R, means it is electric field is independent upon R. So the graph will be this like, that is straight line parallel to this x-axis, means to the distance axis. So it is your second application. Now come to the third application. For the third application, electric field due to uniformly charged thin spherical cell. So here you see it is the spherical cell. Cell means inside each vacuum. It is the spherical cell. It is thin. Thin means inner radius and outer radius, they are almost same. This thickness is very small. So first I want to find electric field outside this cell. Electric field outside this cell. If you take, it is the point P at a distance r from the center of the cell. Here you take the distance of the point where I want to find electric field from the center is smaller. That means smaller more than capital R. And you consider this cell is positively charged. And that distribution you consider it is uniform. So to find electric field at here, you know, you apply the application of Gauss law, you have to consider a Gaussian surface. And by symmetry here, I will consider the Gaussian surface as the sphere and the point P lying on its surface. So at this point, what is the direction of the electric field? It is the direction of the electric field as it is positively charged. Area vector, this one. At every point you can see the redirection of the electric field and area vector is in the same direction. That is here E vector and area vector are in the same direction. That is radially outward. Here also on this Gaussian surface, electric field and area vector also are in the same direction. And due to symmetry, at every point on this Gaussian surface, that is electric field has the same magnitude. So you first find what is electric flux by surface integral method, E vector dot ds vector. So this is equal to, and you find here electric field and area vector are in the same direction. That is E ds cos 0 degree, that is same at every point of the Gaussian surface, that is ds integration, that is E into s, that is E into what is this surface area, as radius is smaller, so it is E into 4 pi, surface area is 4 pi r square. It is your equation number 1. Now you apply Gauss law. Applying Gauss law, phi. You consider the net charge on this cell is Q. So phi is equal to Q by epsilon 0. You see the whole charge is within this Gaussian surface. So I have written I is equal to Q by epsilon 0, where Q is net charge on the spherical cell. From equation 1 and 2, from equations 1 and 2, you write E into 4 pi r square is equal to Q by epsilon 0, or E is equal to 1 by 4 pi epsilon 0 Q by r square. So you see, it is your equation number 3. You see, this expression is for electric field at any point P outside the spherical shell. So this expression looks like point charge expression, electric field due to point charge, and as if the whole charge is concentrated at the center. So you remember the electric field due to spherical shell at any point outside is equivalent to point charge expression, electric field due to point charge, as if the whole charge is concentrated at the center of the cell. So now you can write, you see, as we got here, E is equal to 1 by 4 pi epsilon 0 q by r square, and q by r square. So q we can write 1, that is 1 by 4 pi epsilon 0. For q you can write sigma into 4 pi r square. Why? As it is cell, so charge is distributed over its surface. So surface density sigma, and this area is, as the radius is r, so the surface area is 4 pi r square. So it is, for q you can write sigma into 4 pi r square divided by r square. So you got, it is sigma r square divided by epsilon 0 small r square. It is another expression for electric field due to the thin spherical shell. So now come to second bit, electric field on the cell, on the surface of the cell. Surface of the cell. That means if you take P point to the surface of the cell, then what happens? You see, then what happens if you take P point on the surface of the cell? That means small r is equal to capital R. By the same method, that is phi is equal to here, by integration method, E vector dot ds vector, you here imagine a Gaussian surface just outside the surface of the cell. That means here small r is equal to capital R, that equal to E into 4 pi r square. Equation 1, let it be equation 1, and applying Gauss law, phi is equal to q by epsilon 0. You see, whole cell is within this Gaussian surface. So charge enclosed within this Gaussian surface is the net charge on this cell. You compare E into 4 pi r square is equal to q by epsilon 0, or E is equal to 1 by 4 pi epsilon 0 q by r square. That is equivalent to point charge expression, as if the whole charge is concentrated at the center. So now come to, and if you put that formula in terms of surface density, then it will be 1 by 4 pi epsilon 0, and q will be sigma into 4 pi r square by r square. It will be sigma by epsilon 0. So it is your electric field on the surface of the spherical cell. So now come to electric field inside the cell. Electric field inside the cell. Electric field inside the cell. You take the point P inside the cell. Let the distance of the point P from the center is r. You consider here the Gaussian surface in the form of the sphere. So here you see it's r less than capital R. Here you first to find by similar method electric flux by integration method. that is phi is equal to cross integration of E vector ds vector, that is E into 4 pi r square, equation 1. And by applying Gauss law, phi 0 q by epsilon 0. And here you see, in this Gaussian surface, there is no charge. It is the vacuum. You see, the charge is distributed on its surface, so no charge within the Gaussian surface. So it is here q is equal to 0 by epsilon 0, that is 0. So from equations 1 and 2, you can write E into 4 pi r square is equal to 0 or E is equal to 0. So here you got electric field inside a uniformly charged thin spherical shell is 0. So if you draw the graph, what will be the graph? You see here. If you take electric field along y-axis and distance from the center, distance of the point from the center, you take smaller, that is along x-axis, and it is your capital R, means capital R is the radius. You see, when small r is less than capital R, that means inside the cell you have no electric field, means electric field is 0. But at capital R, means on this surface, you got electric field is E is equal to sigma by epsilon 0. That is 1 by 4 pi epsilon 0 q by r square. On the surface of the cell, you have electric field 1 by 4 pi epsilon 0 q by r square. That is your sigma by epsilon 0. But also it is for r is equal to capital R. For r less than capital R, then electric field is equal to 0. When r more than capital R, E is equal to 1 by 4 pi epsilon 0 q by small r square, that is sigma capital R square by epsilon 0 small r square. So when small r is capital R, then within capital R, that is when r is less than capital R, electric field is 0. When small r is equal to capital R, electric field is sigma by epsilon 0, that is maximum. When you compare this with this, then you see it is the maximum. Then after capital R, means when small r is more than capital R, that is outside the cell, that is inversely proportional to small r square. So the graph will be like this. Electric field is inversely proportional to small r square. So this completes your chapter number 1. So here is the homework for you, that you complete all the NCERT exercises along with NCERT examiner questions.